Hello again. So far we have defined a probability space with probability measure and so on. Then we defined one single random variable. Then we worked on functions of this random variable. Then we went to two random variables. And then we have looked at functions of that, joint moments of that. In this chapter, we want to generalize all those things that we have learned into a vector of random variables. Just instead of two, we may have multiple random variables, x2 up to xn. And we'll see that there is nothing new, just as a simple generalization. So instead of having one distribution of one random variable or distribution of two random variables, we have joint distribution of multiple random variables. And we will have sequences of random variables. So here, a sequence means that a random variable at time 1, random variable at time 2, and so on, xn, and it continues. So these random variables the index could be time, or could be the pixels in an image, or it could be different data you get for different individuals, or different samples of for different entities. The entity could be time, or individual people, or it could be different pixels, and so on. So the outline of this chapter is that we'll first define sequences of random variables, which is a stochastic process. Then we will learn about transformations of these random variables. This is nothing, just is generalization of what we have learned for 1 and 2 random variables. We defined independent random variables. We will review the minimum variance linear estimator as a generalization of what we have learned in the previous random variable. And also I will introduce the notion of complex random variables. And don't be scared, because complex random variables are not complex. They're like, a complex number is like two numbers together. And this and that. We'll then work on correlation and covariance matrices of these random variables, because if you have a random vector, then we could define the mean of this vector, but also we could define covariance or correlation and matrix associated with that. So this is something that we'll look at then. And the properties of these correlation matrices and covariance matrices are very interesting, and there is lots of applications in data processing, in signal processing, image processing, and so on. Then we will generalize what we have learned for conditional densities of two random variables. Here we'll work with conditional densities of like one vector given another vector, and so on. So we'll generalize various possible generalization and learn how to generalize. This is the thing we want to learn. And then we will look at the characteristic function. This is the same concept we have learned before, but in the case of instead of working with just one or two random variables, we may work with one or two random vectors, or even sequences of random variables. And then we will look at the mean square estimation. We'll talk about linear estimation, orthogonality principle, nonlinear mean square. So this is basically the generalization of the last items in the previous chapter. And we look at the linear transformations of a set of random variables as examples. So basically, this chapter is there is no new concept, but we want you to be able to simultaneously work and manipulate with several random entities, because like this is what most of data analysis and so on is that. So we don't deal with two numbers, we deal with multiple numbers at once. So the learning outcome in this chapter is that the student should be able to determine and use the joint distribution of random variables as random vectors or random sequences. They should be able to characterize them, apply their joint probability distribution function, employ their marginal, conditional distribution. Whatever you have learned to work with two random variables, you'll be able to do with different portions of a random vector sequence. Determine the distribution of various functions of these random vectors and so on. Identify independent random variables, employ correlation covariance matrices, determine distribution using characteristic function and vice versa, and apply concepts of estimation theory. There is a couple of graduate course on estimation theory. What we have here is enough for you to go and learn those theories by yourself.